Continue our discussion of Chapter 4 on fluid kinematics, and we're going to talk about Section 4.2, which is the acceleration field, and then we're going to finish off talking a little bit about Section 4.3, although we've discussed almost all of the concepts that were introduced in Section 4.3 in Vodcast number 12. That will leave us with having completed our second vodcast for Chapter 4. Our third and final vodcast for Chapter 4 will cover Section 4.4, which is Reynolds transport theorem, and it ties up a lot of the math and physical concepts that we have discussed so far. All right, so when we talk about the acceleration field, the first thing I want to do once again is to refer you to your textbook, and this is page 171. We begin to talk about something called the material derivative, or it is sometimes called the substantial derivative. And I'm just starting up the document cam right now, so it'll be up in just a minute. The material derivative which is also called the substantial derivative, is a definition which basically creates a complete differential equation comprised of all relevant partial derivatives. So if you think about an equation in several variables, so for example, last time we talked about velocity being a function of x, y, z, the spatial coordinates, and time, we can come up with a derivative of velocity with respect to some other variable, possibly time. Let's go ahead and just use it that way because that's the easiest way to think about it, as being the sum of some partials. And when I talk about the sum of the partials, in order to include the all of the directional components, we would take the unsteady portions, plus we would take the product of the derivative of the vector with respect to a spatial component multiplied by the partial of that spatial component with respect to time. And you can see that just algebraically the dx's here would cancel out. We'd be left with a dv dt, but it's a very specific dv dt. And we could continue that with the other two coordinate directions. And in that way, we will have something that expresses all of the changes with respect to the original variable. All right, now if you continue and you look at these variables, what you'll see is that if you have a dv dx and you have a dx dt, we previously called that, that is the time rate of position change in the x direction. We referred to that as u. This, similarly, would be equal to little v, and this would be equal to w. So we could write that equation for acceleration in terms of uv and w, as long as we keep in mind that we still have the velocity. And then we could split it up into directions. So we could look at a sub x. So in other words, we're not talking about a vector, but we're talking about the acceleration in the x direction, or the component in the x direction, as being del u del t, or partial of u with respect to time, plus u times del u del x, plus v, which is del u del y, plus w times del u del z. And we can do similar in the y and z directions, okay? All right. So when we look at that, we can then use this definition. We can say A then, that would be the vector, is equal to capital D vector V, capital DT, where the D operator means the material or substantial or substantive, sometimes it's called, derivative. So physically, the interpretation is we are taking into account all of the changes in all of the spatial and time coordinates. Mathematically, what we're finding is that it's the partials in each of those directions. So we can take a look at this, just continuing this discussion a little bit, and we can say that D of whatever our variable is with respect to time is defined as the sum of those partials. I'm just going to write this out once. This is actually stated really, I shouldn't put that there. This is actually stated really clearly in your textbook, but I just kind of want you to get a feel for what it looks like. And then, of course, we've got the W del whatever over del Z. All right, so we're looking at all the directions and time. And to simplify that, what we can recognize is that we actually have a gradient times a velocity here. Remember, it's the dot product of the velocity, u sub I, v sub I, or v sub j, w sub x, dotted with the d function x, d function y, d function z, which is the gradient. So we can further say that the substantial derivative of that function with respect to time is equal to the partial with respect to time plus the dot product of the velocity and the gradient of whatever that function is. And this is sort of the hot equation that we need to work these problems. So if you look in your textbook, that's actually here on page 172. So we can see that we sort of backed into this idea of a dot product. We didn't really necessarily know that at first, but as we proceeded along with our work, we can see that that's what it is. Or we can go backward and kind of do it through the chain rule, whatever the function is. So in other words, if we want to find, if our function or our property is temperature, we can do the same thing with temperature. It's always going to be velocity times the gradient of temperature plus the partial of the temperature with respect to time, or whatever the property is. So in other words, the parentheses are just to fill in the blank for a physical property of our fluid. All right, and so then we have a little expression here where we have a velocity, which is an x direction velocity, and so we can do the same thing, come up with the substantial derivative or the material derivative and compute what our acceleration is, which is actually what our homework will be tonight. And I'll work a problem like that for you in the homework. All right, now there's a couple of ideas that we need to illuminate here. And one is the idea of change with time, unsteady effects, and convective effects. Okay. This blue marker bleeds through the paper pretty well, so I need to shape it up. Okay, so let's talk about unsteady effects and convective effects. The unsteady effects are the portions that have to do with anything that changes at a particular location with respect to time. Changes in a property at a given location with respect to time. Now, it doesn't mean that nothing changes with time if there are no unsteady effects, but they are the particular types where we have a local acceleration or a local change. So for steady flow, if it's so, I'm talking about the opposite of unsteady. So for steady flow, the time derivative is 0 throughout the flow field, and this local effect vanishes. But physically, there is no change in the flow parameter at a fixed point if the flow is steady. That's kind of the kicker. So you can have changes over time, but at a particular place, if there are changes in a place over time, then that indicates an unsteady flow. So if the flow is unsteady, whatever property we're looking at, whether it's velocity or temperature or whatever, at any location may change with time. And your authors on page 174 give you an example of an unstirred cup of coffee that will cool down because heat is transferred to the surroundings. So there is, in that case, a del temperature, or d, temperature dt, okay? And that would be equal to the del t plus the gradient, because there is that gradient, and this is actually stated, should be v times del t, okay? And there will be that as in terms of a steady flow. So in other words, there really is no flow. The velocity is equal to 0, but you're still going to have a change in temperature with respect to time. All right, so if velocity is independent of time, that means that velocity is equal to 0, there could be a local acceleration. And the local acceleration term, because acceleration, as you know, is equal to dv dt. So we can go through the substantial derivative and express this. And we will have changes, we can have changes, even if there's no change in speed, for example. You can have changes based on the location or changes based on the nature of that relationship. Okay. Now, the next, when we talk about convective effects, what we're talking about are changes of the property with respect to space. Okay. So unsteady with respect to time, convective with respect to space. Okay? So basically, when you have convective effects, you can have a time rate of change, whether the flow is steady or unsteady, but it's due to convection or motion of a particle through space where there's a gradient, rather than just changing over time for some different reason. So the portion of the acceleration that's given by the gradient term, the v dot del, is the convective acceleration. So this is the time portion, and this is the unsteady portion, and this is the convective portion of the acceleration. Now, in your textbook on page 175, they give you a couple of pretty good examples. They talk about the steady state operation of a water heater, and they also talk about uniform steady flow in a variable area of pipe. If you take a look on the bottom of that page, let's take a look at the pipe, for example. Okay, this is just a rough drawing where we have a neck and then we have a flare. All right. Now, if we have a uniform steady flow in a variable area pipe, what happens? The velocity here, first of all, it's all x directional velocity. We'll call this u. This is equal to some velocity at 1. We have a different u here, which is, let's just call it v2. And because that area is smaller, v2 has to be greater than v1. And here, where the area is greater, call that v3. And if it's the same as v1, they've actually drawn it so that it's the same area as v1, it will be equal to v1, which is less than v2. And that all has to do with the spatial arrangement of that pipe. In the water heater, they talk about a path line as the water comes in cold and enters hot, and so the parameter changes. You could think of it changing with respect to time if you're following that path, but if you're looking at it in streamline, it's changing with respect to location. All right, so in general, the most general form for equation for acceleration of a fluid is equal to the material derivative of velocity with respect to time, which is going to be equal to the partial of velocity, the partial change of velocity with respect to time, plus the velocity times, or dotted with, the gradient of the velocity. And so we get the del V del T, plus we get the same terms, the U, and then the partials in each of the spatial directions. Okay. So we take into account the convective and the unsteady effects. Now, there's an interesting thing. This is broken up into basically, you could think of it as being time, I, J, and K components. We can also take a look at this along a streamline. And if you remember that a streamline is a line that is everywhere tangent to the velocity field, acceleration along a streamline, or for a streamline, let's put it that way because we're really talking about a field, can be thought of similar, let's say in a similar manner to normal and tangential acceleration. Now, you remember when you were in dynamics or physics that prior to, we could define acceleration a couple different ways. We could say acceleration, first of all, we know it's dv dt. But if we're talking about I, J, and K, if we're talking about Cartesian coordinates, we can say that acceleration is acceleration x, I, plus acceleration y, j, plus acceleration z, k. Or if we're talking about normal tangential, we divide the acceleration up into some sort of a change in time, which previously we could say, I guess I would say dv dt, and that would be normal, or excuse me, tangential, plus the change in direction, which turns out to be a v squared over r, or a radius of curvature in the normal direction. All right, so along a streamline, let's say, for example, you have fluid flowing steadily through a pipe. Maybe it's a curved pipe, it's an irrigation tube, for example. And so here you have a streamline which is everywhere tangent to the velocity, and we will call the unit vector along the streamline S sub cap, or S super cap, I guess I would say. That would be the unit vector along a streamline. And perpendicular to that, we would have a unit vector N super cap. And the N super cap then is the unit vector normal to, or perpendicular to, a streamline. So your authors go through the derivation, and they write out the equation a couple of different ways. But in the middle of page 179, they write it out in this form. they say acceleration for streamlined components A is equal to V del V del S times S supercap plus V times V del S del S. And then they take a limit and they do a little bit of breakup into convective acceleration, and they come up with equation 4.7, which is not actually complete. 4.7 talks about steady flow, which means that we don't have any time changes based on location. So I'd like to write it in a slightly more general form. And then this is quite usable to find out the actual expression for those components of acceleration. So they write that A is equal to V dV ds S cap plus V squared over R times N cap. All right, so this does not take into account or doesn't break out any unsteady effects or any time effects. So if in fact V is a function of time, this equation is not valid. So I'm going to just add a little bit to it so that we can make it valid for a case where velocity is a function of time. And so I would call that 4.71, right? It's not in your textbook. But so acceleration in a more general form would be, let's just say, A sub s times s supercap plus A sub n supercap. And we could write then that A sub s is equal to V dV ds. Let's also include the dV dt term. And A sub n then is still equal to V squared over R. So this is the change in direction, and this is the change in, well, it can be the change in speed for that particular, along that streamline. And this is something that will come in handy pretty often, because this is a very typical designed incompressible flow. So if we wanted to combine this into sort of a final version, we could say then that A is equal to V dV ds plus dV dt S cap plus V squared over R N supercap. And that's a very useful equation. All right, now we already discussed, before I do a problem showing you how to use this, section 4.3 talks about control volume and system analysis. And we've already discussed these two ideas. And we've related this to a fixed place. And we've referred to it as Eulerian. Okay, and the control volume does not have to be a fixed volume. It can be expanding. But we're talking about some sort of a volume or some sort of a place. A system is a fixed mass or fixed particles or collection of particles. And to analyze that way, it's referred to as Lagrangian. Right? And what section 4.3 does then is set us up for section 4.4, which we'll discuss next time, which the title of which is the Reynolds transport theorem, RTT. And Reynolds transport theorem is really the bridge between looking at a system and looking at a control volume. So Reynolds transport theorem is a way of using the material derivative, which we just learned, to look at a fixed amount of mass, or a fixed mass, as it passes through a control volume. So it gives us the most complete picture that we can in terms of fluid analysis at this point. So that's what we'll do next time. But for now, let's go ahead and work a problem. And the problem that I've chosen to work for you is problem 4.44. So switch back to my document cam, and I'll put that number up, and then we'll take a look at the problem in the textbook. 4.44, and we'll run the analysis. Okay, so the problem's 4.44 is actually on page 200 in your textbook. Okay, and let me zoom in a little bit so you can see it. All right. So there it is. All right, here in problem 4.44, we have water which flows through a curved hose, and it is flowing through with an increasing speed of V is equal to 10 t feet per second. Okay. Now, the first thing about this is we need to recognize that it is not a steady flow problem, is it? It may not be random, but we do have, since velocity is a function of time, we're going to have to take that into account. The other thing that's interesting, and this kind of makes sense, if water is incompressible, which it is for the most part, we have the velocity increasing, but the velocity, if this hose has the same diameter or circumference throughout, which it appears to, that means that the velocity at a point is going to be the same at a given time. So the velocity of the water, I'll go ahead and draw the hose. We have this curved section like this. So at a given time, when we say t equals 1, the velocity here and here are going to be the same. And at t equals 2, the velocity here is going to be the same as the velocity here. However, as time increases, the velocity increases. So let's go ahead and draw our velocity vector. And it tells us that the radius of curvature is 20 feet. Okay? So there's our drawing for the problem. Water flows through a curved hose as shown in figure 444 with an increasing speed of v equals 10t, where t is in seconds. For t is equal to 2 seconds, determine the component of acceleration along the streamline. What is that? That's a sub s at t equals 2 seconds. That is the first thing that we want to find. B, we also want to find the component of acceleration normal to the streamline. So that would be a sub n. One would assume at t equals 2 seconds. And finally, the net acceleration, which is going to be a subtotal. Now, we haven't really done this yet, but in physics and in dynamics, you'll remember that since s and n are perpendicular to each other, that magnitude is going to be equal to the square root of a sub s squared plus a sub n squared. So we're going to find those two. We are golden here. All right, so going back to the equation that I wrote as the most general form of the equation, we can say a sub s, we need to take into account the time effects, and we need to take into account the spatial effects. But there are two ways we can look at this tube, and we can see that there are no spatial effects, that dv ds is equal to 0. The other way we can see it is by looking at the equation. V is not a function of s, is it? So dv ds mathematically is equal to 0, and dv ds physically is equal to 0. So that means that a sub s is equal to the first derivative of this with respect to time, which is 10 feet per second squared, right? And that's going to be not just at 2 seconds, but for all time. The velocity is increasing at a steady rate. That means that the acceleration is constant. All right. Now, that tells us then, that's kind of, we got off the hook easy there. A sub n is going to be equal to v squared over r, which is 10 feet per second squared, divided by the radius of curvature of 20 feet. So 10 squared is 100. It's feet squared per second squared, divided by 20 feet. 20 goes into 100 5 times. Feet goes into feet squared, feet per second squared. So we have that our normal acceleration is 5. Oh, you know what? That's not right. I plugged in the wrong value here. I apologize. This is the acceleration, isn't it? And it does make sense that the normal acceleration is going to be changing because the velocity is changing, so it's a function of velocity. Excuse me, let me start over. So my a sub n is my v, which is 10t feet per second, quantity squared, divided by my r, which is 20 feet. So my normal acceleration then is 100 t squared, feet squared per second squared, over 20 feet. So what does that turn out to be? Well, this is 5 t squared, feet per second squared. I've already taken care of those units, so we've got that. But at 2 seconds, what does that mean? So a sub n at t equals 2 is going to be 5 times 2 squared, which is 2 squared is 4, and 5 times 4 is 20 feet per second squared. All right, so if I were to write that as a vector in SN coordinates, I would write the acceleration is equal to 10 s sub n, or s cap, plus 20 n cap feet per second squared at 2 seconds. All right. So it asks me for magnitude then. The magnitude of the acceleration is square root 10 squared plus 20 squared, square root 100 plus 400, square root 500, and I could break that out, which I probably should because I don't know what my calculator is. So this would be 25, let's see, if we break this down, we get 2 times 250, which is 10 times 25. So I have the 25 comes out as 5 times the square root of 20, and that's 4 times 5. So that comes out, so it's 10 times the square root of 5 feet per second squared. That's the magnitude of my acceleration. And that's going to be somewhere, this is about 2.2, so this is going to be about 22 feet per second squared. Now, when you have your calculator, you'll get some decimal places in that. It's a little bit higher because I just said that the square root of 5 is 2.2, but it's just between 2.2 and 2.3. All right, so what's my direction? Well, I know that my a sub s is equal to 10 feet per second squared, and my a sub n is 20 feet per second squared. So my net acceleration is going to be, if we want to reference it from the streamline, theta equals, what's this? We have adjacent, opposite, tangent to the -1 of the opposite side over the adjacent side, which is, theta is the inverse tangent of 2. And I don't have my calculator with me, but this is twice as long, and theta is going to be approximately equal to 66 degrees when referenced from the streamline. Right. And like I said, when you have your calculator, you'll get an exact number for that. That's just a ballpark. All right, so ladies and gentlemen, that's it for Vodcast number 13. We have finished sections 4.2 and 4.3, and next time we will do section 4.4, Reynolds Transport Theorem, before we finish chapter 4, and we are ready to do exam number 2. Thanks. See you next time.